Yes, I wanted to start with some, well, first looking at what we did last week. So a refresher. So we had a look at what we call Hutton's razor. It's the smallest language to demonstrate an idea. So in this instance, we wanted to talk about typing. So we had two type of values in our language, natural numbers and Boolean expressions. And we could add them, we could do everything else and so on. But the problem was that the types were not enforced in the syntax of the language. And so when we wrote the evaluator, we ended up building everything in this maybe monads, where we're just unwrapping a lot of nonsense. And even if we get a value, sometimes it's a value of the wrong type, and then things blow up. So we saw that instead we could have a strong invariant enforced directly into the syntax of the language, saying that we only consider well-typed expressions. And so when we do that, the type of values is entirely determined by the type of the expression, and suddenly the evaluator doesn't need to deal with errors anymore because there are no errors. All the errors are gone. Of course, there's no free lunch, right? That means that the error checking needs to happen somewhere else. But once you've carefully checked that your untrusted user input is error-free, you get access to this nice evaluation function. So what does it mean for an untrusted user input to be error-free? Well, we cooked it this way last time. We defined erasure that strips away all of the type information. And then we said that a function is well-typed. I can't remember. A term is well-typed. Where is it? Here. If it could be obtained by erasing a type term. And then we saw that that actually makes sense. We can actually take a user input and transform it into something that's well-typed. And we targeted maybe because it's just a bit easier, but then discussed the fact that we could have decidability or something a bit more constructive than just prove that any typing would fail, as in a proper type error.
Yeah, so there's a slogan that goes with that, which is parse, don't validate. So rather than just saying, here's a lump of untrustworthy stuff, is it okay, yes or no, right? But leaving the stuff as it is. What are the consequences of that? Yes. Well, maybe you feel slightly safer doing something which on the face of it looks dangerous. But if you haven't kind of refined the dangerous thing into something which is by construction safe, you're missing a trick. That's to say, my slogan for this has always been learning by testing. That's to say that the whole point of the testing is to actually learn something. And how do we represent that, the outcome of that learning? So here, it's, we actually generate the thing which runs safely.
Yeah, and it's all about this idea that started actually, in CS106 already, of layers of abstraction. So at the end of the day, everything is just byte arrays. But of course, if you are only manipulating data encoded as byte arrays, you jump out the window. You want to have like these nice representations in between that give you a lot of guarantees. And then, well, there was this title, but we did nothing of that. It's going to come back this week. Okay, so some food for thought. So last week, we were always inferring what the type of an expression was. As in the function was going from a row expression to maybe a type together with the type term that erases down to the inputs. But what if you have overloaded constructs like plus that work for all numerical types? And this time around, you don't just have nats, you also have ents and floats and so on. Then that inferring behavior doesn't work anymore. From just seeing plus, you don't know what the return type should be. Last time we saw plus, we said, okay, it has to be a nat. And then we checked that the subterms were nat and so on. So of course, you can think of coping strategies. You might infer the type of the two subterms, then make sure they have the same type, and check that it's a numerical type, and then decide that this is the output of the plus, and so on. But we're seeing already that what if you're not able to infer the type of one of the sub-expressions, for instance? But you could infer the type of the other one, telling you it's a float. So therefore, you know the only way the plus is going to be a well type is if the other branch is also a float. But because you're insisting on always coming up with the information yourself and then double checking that everything is consistent, you're losing the ability to type some weird looking programs that could actually be typed. So then the idea is to have not only type inference, where you're insisting on guessing and then verifying that the guess is what you wanted it to be in the first place, you also have checking, where you know what type you want the expression to be, and then you're pushing that information down against the syntax. And sometimes that information will be propagated to sub-expressions, sometimes it won't, but at least you're making use of that as much information as possible, rather than insisting on guessing every time. So yeah, that was the first thing. The other thing, which is somewhat related, is that we could have proven that if you have two type terms and they raise to the same underlying row term, then their types are equal. And that's because our language is very simple and everything is just a Boolean or a natural number. But in practice, it's not true. So you could have as soon as you have polymorphism, for instance, you could have the identity function. You could see it as the identity function on natural numbers. You could see it as the identity function on Booleans. And it's not technically the same term, but it erases to, well, it is technically the same term, but it doesn't have the same type. So you're not seeing it the same way. And because in our language, we don't have polymorphism, there's actually no way to reconcile these two views. So the types are not equal anymore. And okay, that seems easily fixed because you can just throw in polymorphism and then again you have unique types because you can say, well, it's just the identity function. Like, I don't actually care about the underlying type of terms that I'm passing to the identity function. But you can't always get away with this and throwing more information and so on. At some point, your type system becomes so powerful that there are just no most general types anymore. So this is an example in Agda. Can you give me the type of this term? So if you use inference, right, it starts with a comma, so it's going to be a pair of something. And then there's a 2 on the left, and there's a proof on the right. Oh, I don't know if you've seen the syntax before. Okay, of course it doesn't want to jump to it. Mm-hmm. It's this less than relation, right? It's saying that 0 is less than everything, which is a fairly good notion of less than. So one proposal is, okay, we could have, it's a proof that there exists a number that's bigger than 0. That type checks, right? But it could also be just a proof that natural numbers are inhabited and 0 is less than like 3,000. Okay, let's get this up, of course, by being too controlling about the inputs. And that's just equally valid. And now there's no dependency between the first element in the pair and the second one. So there's no way to find the types that more general than these two and say, okay, there exists I don't know, a natural number that's both 2 and 3,000 somehow.
Yeah, so the point is that these things admit arbitrary patterns of dependency of the type of the second thing on the value of the first one. And you can't figure out what the pattern of dependency is from just one example of it. So in this situation, type inference is notoriously hopeless. But type checking is just fine, because then somebody tells you in advance what the pattern of dependency is, and you're just checking that that pattern's being followed.
Yeah, so typically what we do in modern compilers is that we have both inference and checking, and then information that's contained in the term. Sometimes maybe a term has been annotated by the user because they're saying, well, in Haskell, we actually do this quite often because when you say 0, it will default to integer, but sometimes when you're building a range, for instance, you want to insist that it's an int or it's something else, right? So sometimes the user explicitly tells the compiler this one is actually of that type. So then that's information that can be bubbled up. And so quite often, I mean, in Agda it's always the case, right? We have these top-level annotations. So that gives you information that can be pushed onto the terms. So you have this interplay of information flow by going down and going up the tree. And whenever they collide, there you're checking that all of the constraints that you've created are making sense.
Yeah.
But quite often you don't have any constraints colliding. You just have information that's coming to you and you're really happy to make use of it.
The way it typically works is that things which look like values that are made from constructors get type checked. So like this thing, the red stuff. But things which look like they might talk about computation rather than values, generally things which involve variables. Right? We tend to do type inference. That's to say, we make sure we always know the types of the variables, and then the types of the variables tell us the legitimate ways in which the variables can be used. So for example, I mean, the classic example is that you figure out, when you're faced with a function application, you figure out the type of the function, and that tells you how to check the type of the function's input and deliver the type of the function's output. So there, when you see things being used, we expect to see type synthesis. When we see things being constructed, we expect to see type checking.
Right, so that's more of the limitations of what we saw last week. And the last one, which is feeding directly into this week's discussion, is how computationally interesting is this language of expressions. Let me find it. Okay, so we have constants of two different types, but they're still just constants. Then we have addition, but addition of constants is, again, a constant. And then we have if then else, but it's branching over something that's ultimately going to be a constant, maybe with some layers of like computations on top allegedly, but it's just a constant in disguise. And then we have two branches. We select a branch or another, but again, they're just constants. And this is actually what T-eval is showing us, right? It's like as soon as you've settled on an expression, I can give you a single Boolean or single natural number that's just as good as your expression, and it's actually already computed. So why would you bother compiling that expression? You already have the value.
I mean, yeah, when you write 2 plus 2 as an expression in C, most C compilers will compile that as 4. The thing will not actually add 2 and 2 at runtime. The compiler will do that.
So what we're going to see today is how to make the language a little bit more interesting and add variables. So variables could stand for user inputs or just some kind of generic computational mechanism, right? If you're going to describe the identity function, for instance, you want to say, well, whatever inputs I get, I will pass it back as an output. So to do that, we're going to start from scratch again. So we have our type of types. I don't know why I left it in, but it's the same as last week. And then we can define what it means to have a context of variables. So here there's some freedom. What we do is we just pick a linear context, and out of habit, because of the typing rules we're used to seeing and so on, they grow to the right. So I'll define this way, where we can have the empty context, epsilon, or we can have or maybe I'll be kind to Connor. And, how can I call this?
How do you, I don't know how you even type that thing. Yeah, thanks.
And if we already have a context, we can extend it with a type to the right. So for instance, all right, and well, let's give an example. For instance, we can have the context that started empty, and then we saw a Boolean, or I should stick with our convention from last week. So I should have deleted that code. So first we bound a Boolean, then we bound
a Pixity declaration.
A natural number, maybe I do, yeah. And then we found another Boolean, whatever, that's good enough, indeed.
You want it to be left associative.
Thank you. Up. Okay. So we want it to be left associative because it doesn't make sense otherwise, right? This is left biased. The substructure is always on the left. Okay, so that's an example. Of course, we can also just have the empty context. And then we're back to last week, basically. We don't have any variables in scope.
The intuition is that time goes from left to right. And the most recently added thing is the most accessible thing to us, and it's the thing on the right. And I teach people to use lists that grow on the right, rather than trying to use usual lists that grow on the left. And then that means they're turning their brain round when they could turn their code round instead, keep their brain the way it is. So, you know, less cognitive load, please. Can we just see what we mean in the program?
And so, of course, this is just Forward's list of types in disguise. But here we have a notation that's closer to the domain. So you can, well, I suppose we could have used patterns, whatever. And then what we want to do is we want to define membership. So how can we say that a given variable is in scope? Oh, okay. One thing I forgot to say is that we don't have any names. We just have types for our variables. And that's because we're in the elaborated syntax where only the binding structure matters. Like whether you call the variable in your identity function X or Y or Z, it doesn't matter. It's going to have exactly the same behavior. It's taking in the input and immediately returning it. So we just throw away all of the names. In a practical implementation, you would want to have the names around at least for error printing for the user. You would want to be kind to your user. Here, we're our own user, so whatever. Okay, so membership. What does it mean for a variable to make sense in a given context? This way, set where. So a variable in context given to us will have this type here. So do you think it makes sense to have a constructor called, let's go here, whatever, in the empty context? If I can type sigma. I should have declared var variable sigma in time. Okay. Yes, no. Well, so the point of a variable, right? As Connor was saying, time is flowing and we're accumulating these binders that we've seen on the way, these declarations of these variables that we've seen on the way. If we're at the start of time and there are no declarations whatsoever, then you just don't have any variables. So this does not make sense. No variables in the empty context.
Right.
And yep.
Yeah, so the point is that we're going to represent variables as the selection of a thing from the context. So you can think of it as a kind of pointer into somewhere that's in this
this sequence. And we're going to say, like, want that one.
Mm.
So,
Uh, so I'll use this. So if we have a non-empty context, oh, I should have add variables for context
Yeah.
also. Variable delta context.
this is traditional to use capital gamma for contexts. Can't remember why.
So if you have a context that we know to be non-empty, and the last thing we saw on the way n is a variable declaration of type sigma, then we can see that the 0th variable, the most local variable, is called sigma. Oh, oh, as type sigma.
Yeah.
It doesn't have a name. Well, it's called 0, I suppose. So
Yes, we're working in the fine Dutch tradition of Nicolas de Bruin. Then we number variables. We say how many things we have to jump over before we get to the one we want. So if we want the thing that's on the top, we have to jump over 0 variables to get there.
and if we have a successor, what does that say? Well, again, it better be a non-empty context. And then I'm looking for a variable of type sigma somewhere in there, and I'm declaring that I'm not interested in this one. It might have the right type. You know, when you're looking for a Boolean here, the first variable or the 0th variable in scope has type bool, but it's not the bool you meant. So you just ignore the type that's here. You have to name it because, oh, I guess, yeah, you do. Okay.
Yeah, you do.
But it doesn't influence the one you're looking for. So you're saying if sigma is somewhere further into the context in the prefix gamma, then it's also in gamma extended with tau. And I look it up by just skipping over tau and looking into gamma.
Yeah. And this is the funny thing. It's strange the way that the notation looks like information coming out, but the way we're talking about it is about information going in. It's like, how do I point to something in this context? Well, I either say it's the thing that I want, or I want to jump over the thing and then keep looking. So we're discussing from the outside in how to make sense of these data.
And when we're looking at Curry-Howard and we're discussing how to encode logic into ACTA, we saw some quantifiers over lists, right? We saw all that says that a predicate applies to all of the values in scope, but we also saw any saying that we can find an element in the list that satisfies a given predicate. So this is just any sigma equals, no, I'm getting it backwards.
Yeah.
Sigma equals gamma in this guys, right? And at the time I had called these here and there to tell you like the variable verifying the proposition is here or it's further down the list. And Conrad already said, well, this is basically just 0 and successor. It's just an index telling you where the proof is, well, the value satisfying the predicate is. And then once you walk down that list all the way to that position, you actually have the proof sitting there. Okay. And then we can define what it means to have a typed and scoped expression. So I'm going to go back to last week. Oh, there was no need to do that. It's not imported. And just do a bit of copy pasting. There we go. So that's what we had last week, and now we want to talk about expressions in a given context. So what do? Well, we just throw in a context, and then all of our existing constructors need to be given a context. So this is the old constructors, and then there's going to be some new constructors.
You could put the context left of the colon.
For now, or even always, yeah.
Even always.
Yeah. I could. Okay. All right, so that's simplifying some of our work because, well, I mean, so that's already a design decision actually, right? You could say, for instance, that you're only able to build NATs in an empty context, but then, like, what's the point, right? It's a language that's not going to have super nice properties, so if you, yeah, if you want to be able to substitute values into a term, which is something we like to do when we do computations, if NAT is only able to allow to appear at the top level, then it won't be able to go deeply nested in terms. So somehow that language will be badly behaved.
Yeah.
Also, there's no reason to arbitrarily restrict this thing, right?
I mean, there's something
Oop.
philosophically unsatisfying about contexts that get modified non-locally, right? It's like time travel.
Mm.
You can't go back and, I mean, also it's just like you don't get to control the context you find yourself in. No. It's something that you expect to grow locally, maybe, but the stuff that happened you can't change the past, is what I'm saying.
Or your context. Yeah, I mean, it's called context because it's surrounding you. Basically.
Yes.
So we can have our constants, we can have our booleans, and then we have a bit of freedom here when we're talking about the sub-expressions. But if I'm adding two numbers, I'm not going to get extra variables on the sides of the additions, right? So I can just keep gamma. And then for the f then else, it's the same thing, right? I know that globally I have, globally, on the outside of the if then else, I have access to gamma. So for the Boolean, I will need to use the, what the heck? Oh, caps lock, I see. So on the, when I'm making my decision using a Boolean, I can only use variables in gamma for that decision. And then on the left and right hand sides, I will have access to no more variables than that. But, and that's the nice thing about it, now we can throw in more variables that are talking about, well, more constructors rather. So what does it mean to use a variable in a given context? Well, I'm going to build an expression of type gamma t. I'm back to using capital letters now rather than Greek. And when, well, okay, I could have this, but this is extremely silly, right? It means I can always magic a variable out of nowhere. So of course, the thing to do is to say, if I have a proof that there is a variable in gamma of type t, then I get to build an expression of type t that lives in the bigger context, gamma. And then a thing we might want to do is lambda abstraction. So we tend to like functions around here. So if you have two types, oh, okay, that's bad.
You haven't given yourself
A type of functions.
a type of functions yet.
So I need a type of functions, no worries. I can just jump back to types. And I'm going to say I can build a function. Oh, it's not like here. So these ones are base types. They're just, their own type is only type, but functions, of course, have a domain and a codomain. So they are taking two arguments. And now, for instance, we can say, this is the type of functions from the natural numbers to, let's say to bool, actually. So this is a type of decidable predicates over natural numbers. Okay. So now I can say I want to build a function from S to T. And how can I do that? Well, a function, it's something that whatever S is passed to it will be able to return a T. So the way you model that is you say, well, I'm going to pretend I got my hands on an S as a variable, basically, that stands for whatever term the caller might give to me. And based on that input, I'm going to produce a T. So I can say, I want a typed expression of type T, where the context is gamma, but now it's been extended with the S I was just given by the caller, except that I've not received it yet. I'm just pretending that I have my hands on it, and then I can do some work. So for instance, I can define bool to nat. So bool to nat. It's a function from bool to nat, the name suggests. And no, it's a typed expression. Yeah, let's do it like that. So I'm saying my definition will be valid in an arbitrary context, which will make it easier to use, basically. Otherwise, I could also just say it's a closed expression, because I know I'm not going to use any of the variables in context. Okay. Can it? Oh, okay. So Ida figured out that the only way to build a function is to use a lambda abstraction. So it put that together, but then it returned constant 0, and that's not what I want to do. What I want to do is use an if then else. And here I'm going to refer to the Boolean variable that I got as an input, right? Because to decide how to convert a Boolean into either 0 or 1, I need to first look at whether the Boolean is true or false. So I can use the variable, and here, thankfully, Agda is able to figure out that proof. And then if the Boolean is true, then I want to return exactly not this, 1, and otherwise I want to return 0. All right. And then I can define double. So double is a typed expression that's valid in any context whatsoever. And it's taking natural numbers to natural numbers. And there is no prize for guessing what it does. Okay, Agda really likes constant 0. It just adds the variable to itself. And there's a single variable in scope, so I know that proof search is going to find the Brown index. So this is the same as lambda x goes to x plus x, right? We're always referring to a variable by counting the number of lambdas we need to jump over to get to the binding site. Here we don't need to jump over anything, so we're looking at 0. Actually, I should maybe do constants. That's this one. For one where we don't use 0, or I suppose if I want to use my existing variables.
I was wondering where the Greek letters had gone.
No. Okay, so constant is a function that takes a value and then returns the constant function, always returning that value. So, I mean, it is quite convenient in functional programming. I don't know how to convince you of that, but it's just a useful thing to have. This is generic enough that, yeah, there we go. Okay. So first, we need to introduce the variable of type sigma. Then we need to build another function. There's not very much we can do apart from introducing the variable of type tau. And then we want to skip over tau and refer back to sigma. So we're using a variable which is not the most local one, and instead is the one that comes before, as it were. And so that's why we have the Brown index 1 in this case.
I don't know. Once upon a time, there was in fact, twice upon a time, but only once worthwhile, there was a television show called Battlestar Galactica, in which human beings are facing off against robots that look enough like human beings that they can be played by actors. And, and they spent a lot of time trying to figure out ways to tell the difference between people who are people and people who are robots. And the catch is that some of the people who are robots don't even know that they're robots. So they're very well disguised. Our colleague, Bob Apke, just suggests that if they can cope with using de Bruijn indices to refer to variables, they're probably a Cylon.
Yeah, so to withdraw the Brown indices maybe,
Yeah.
but here we actually have membership proofs, right? So it's not too bad. So it's,
Yeah. Oh,
like the type system is keeping you in check.
yeah, once the examples get big, I mean, it's marvelous that they're precise, but for human beings, they're hard to read.
Okay, I think we might have just enough time to do the semantics because there's a
Yeah.
lot of copy pasting. So,
I was wondering where application got to.
oh yeah, there's no application.
Yeah, we want to actually be able to use these functions, not just build them.
Well, sure,
do
if
it.
you want, we can add application. So, what does it mean to apply a function to an input? Well, you better have a function. Oops, I was gonna screw this up. You have a function from S to T, and then to have a valid input, well, you need a value of the input type, and then you get a value of the output type. And this is a bit funny in a sense, right? It's like a term of type function behaves a little bit like a function. But this is just syntax, right? There's no actual function in there. It doesn't compute. It's just storing values, just to be clear. It's just a neat little thing. And for instance, we can compute 4. Or, if I can get my stuff together, it's an expression. Well, let's put it in the closed one, this one, for no reason. It's the double of a nat called 2.
Yeah.
Oh, it's the application. Okay. I'm so used to, in Agda and in Haskell and all languages, right, application is silence. You never write it down. It's just the space here. So out of habit, I didn't write it. I just called double. But of course, in our syntax of expressions, you cannot use just white space as being a constructor. Although there was an April the 1st tag sent at some points to allow you to do that.
Yes, there are Agda programmers who have a deep knowledge of all the different Unicode non-standard whitespace characters.
And one of them tried
would
to
they
make them
please
rebindable.
stop?
Yeah. All right, let's get to the semantics. Should be fine still.
Yeah.
So I'm going to split my thing in two and go to last week. Oh, of course, I closed this. Now I need to reopen it. Doop. Up. Tval. If you remember, we defined the type of values by looking at the type and translating it into an Agda type. And now we have an extra type, fun st, and we need to explain what it means in terms of Agda values. And of course, we're going to use the type of function from S to T. But we need to translate these subtypes into set themselves. But I don't think that's necessarily super surprising. And then we have cval, which is similarly taking a context and giving you a set of values. And this one goes by induction on the context. Of course, it's picking horrible names. So if the context is empty, there are no variables in scope, so we don't need any value. How do we say that we don't need any value? Well, we have the thing that's trivial to build, if I can type it. And it's not in scope. Base, top. Oop. So this is the trivially true proposition. If we're to use the trivially false proposition instead, to say, oh, there are no such values, whatever, then we would never be able to build a meaning for a context, because at the end, we would always need to put in a proof of false. So
Yeah. It's always worth thinking, what's the right way to do nothing?
yeah.
Do we want to make the empty context, do we want to make sense of the empty context as something impossible or something trivial? Let's go with trivial.
And the hint is in the step case, right? When we're saying when we have a context of values, values for our context is gamma s. Well, we want a value for s, and we want a context of values for gamma. So there's going to be times, and typically, I mean, this is also 1, right? There's exactly one value in the top type, and 1 and times are usually going together, with sum and 0, or union and bottom usually go together. So here on the left, we're going to have a C-val for gamma. And here on the right, we're going to have a T-val for S, because it's a type. So this is to say, this is all T-val gamma in disguise. So just to say that these predicate transformers that we've seen are really useful, like across the board. Example of a C-val. Okay, that's, I don't know about that, but we can have a C-val for the type with a bool and a nat. So if I look at this in here, it is an iterated product of nothing at the start, well, proof of unit, then I need a proper Boolean, and then I need a proper natural number.
That's so readable.
Yes. Oops. Oh, there we go. Okay. And then we need to define T eval. So I'm going to do a bit of copy pasting. So the typed evaluation. And I'm going to add a control. Okay, now I need gamma. Right. So this was the type for typed expressions that were all closed. So there was no context. So there was no notion of the meaning of the context. But now we need to also talk about the context. So no worries. We can just add it here. And of course, the meaning itself is going to change. Now we have variables, so we need values for them. When we were talking about functions, right? And if you remember, the functions are pushing their input into the context by saying the caller is responsible for passing me this value. So when you're describing the semantics, it's going to be the same thing, right? You're not going to do cval times t, because that would put the responsibility on you to deliver both the values for the context and for the type. But actually what happens is that the caller is supposed to give you the value for the variables, for the unknowns, and then based on that, you're willing to deliver the value for the expression. And of course, it breaks everything. I'm just going to quickly put these in, and then in the recursive calls, so I know that this is valid because if you remember when we defined if then else, add, etc., the subterms were using exactly the same context as the overall expression. So the environment for that thing is enough to deliver.
Yeah, so that's a careful use of terminology. Context tells you types of variables. Environment tells you values of variables.
Okay. So here I have a variable of type t in gamma, and I have a context of values for gamma. So of course, I can produce a value of type t. That's done by looking up the variable in the environment. So let's see, if I have var gamma t and c val gamma, I can get t val t. Up. For t. Lookup. Oop. All right, so I have my x and my n. And here, if I look at the stuff in scope, well, variable is defined by as a data type, as a family, right? Saying it's either the 0th one or the successor one. An environment is defined by recursion on the context. So the only way to get environment to reduce would be to inspect the context. It's a bit annoying though. I might as well match on the variable because the variable forces the shape of the context. So if I split on the variable, it's either the 0th one, and then I have my value sitting here, ready to be used, and this is not going to be in scope. It's also one of the few cases where...
Why don't you just pattern match on the thing? I'm going to be done with it.
Yeah, okay. Yep. So my environment is something, I don't care what, and a value of the right type, so I can return it. And then if it's a successor, again, it forced the environment to be the context to be non-empty, which means that the environment is a pair, but I'm looking further into the context. So that means I need to look further into the environment. So this time I'm going to ditch the rightmost component of the pair and just look up the variable recursively. And so now here, I can just look up my variable into the environment. Okay. For lambda, so I call this B because it's the body of the lambda. It's just like standard conventions. You can see that now I have the body which lives it lives in an extended context and returns a value of type t. We want to produce a value of type t under the assumption that we have access to a value of type s. So this is by definition of t-val saying the type of values for functions is literal functions between the various types of values. So I can bind my s with an agda lambda, and now I can call t-val recursively on b. I know that b has type t, so it will deliver the right t-val. And now I need to build an extended context because b was defined as this. I need to build an extended environment because b was built into an extended context. But luckily, I have all of the back for me, right? I have the environment for the surrounding context, and the caller just gave me little s of type t-val s. So I can build an s here. And the application, well, let's just call f the meaning of f and t or this is painful because now t is not super uniform. It has multiple meanings.
It's also scary to call the thing
Fun, art. Yeah, it's really annoying. Okay, let's do it like that. So I evaluated my function in the given environment, and it gave me an actual function, right? Because the syntactic lambdas got turned into semantic lambdas, like agda lambdas. So now it's just waiting for an s. And of course, when I'm applying a function, I need to provide the function with a sensible argument. And by evaluating that argument, I got a value exactly of the right type. So now I can just apply the function to the arguments, and that gives me my definition. And so now, with the 45 minutes that are left, I can t-eval 4 in the empty environment. Oh no, that's the empty context, so the empty environment is trivial. Okay. So just to be clear, if you remember, 4 was defined by applying double to 2. Double was the function, adding a variable to itself, and 4 was crucially defined in the empty context, meaning the environment we need to provide for evaluating is trivial. And so now we can run 2 plus 2, and we get 4. Or rather, we eval lambda x plus x applied to 2, and we get 4. And that's it for today.
Cool.